Hi everyone, my name is Keir Rogers. I'm a postdoc at the University of Toronto. Very pleased to show some of my work, which is on the theme of cosmological tests of the fundamental nature of dark matter. So the problem of dark matter is, of course, even older than the Institute of Astronomy. And in particular, although we have the velocity dispersion measurements of galaxy clusters from Zwicky in the 1930s, it is really the measurements of the rotation speeds of galaxies by Vera Rubin and collaborators in the 1970s that conclusively demonstrated this, the existence of this missing matter, that there's more matter in the universe than we can see. And we now have, over 50 years, built up multiple independent astrophysical probes that all confirm its existence. But the fundamental particle or particles that make up dark matter remain a mystery. We've built, in terms of peak spend, multi-billion pound experiments to detect the historically preferred particle candidate, the WIMP, the weakly interacting massive particle, and high-energy colliders and through direct and indirect detection, but no signal has been found, and much of its parameter space is now excluded. And so that's motivated this shift, this paradigm shift in the dark matter community to consider theoretically more motivated alternatives, but which therefore need very different experimental approaches to detect or exclude them. So here I'm showing you a top-level schematic view of the dark matter model space, where I've ordered different class of dark matter model by the mass of the new fundamental particle that they would require. If you like, you can imagine primordial black holes and other machos existing off to the far right of this plot.
It's going to automatically move. Sorry.
Oh dear. But in particular, on the far left of this plot, there are many models. Thank you very much.
Just don't press it for too long.
Okay, thank you very much. On the far left of this plot, there are many models where the dark matter will be made of some particle lighter than the WIMP, which has these masses around a GeV to a TeV in mass. Vid talked about warm dark matter, which would be some thermal relic particle with a mass around the KeV scale. And in particular, I want to talk about a candidate called the axion. So here you have a particle lighter than the mass of about 10 electron volts. And in particular, in many high energy theories, it's well motivated to have an axion, which I'll call ultralight, which I'll define to be a particle of a mass less than 10 to the minus 18 electron volts. And now, by the uncertainty principle, the mass of this particle is so light that its de Broglie wavelength becomes astrophysically sized. And so you will have very distinctive wave-like phenomena manifesting on cosmological scales. And so what are the features of this ultralight axion paradigm, which I'll often call fuzzy dark matter? Well, here are some results from some cosmological simulations of a mixture of cold and fuzzy dark matter. So I'm going to drop a very strong assumption we often make, that the dark matter consists of only one new species of particle. We know that the standard model affects cosmology through both atomic and neutrino matter. And so we'll allow for a mixture of some massive particle, which could be a WIMP or a heavy axion, behaving like CDM, and a population of these fuzzy dark matter particles. So slice through a dark matter simulation, CDM on the left, FDM on the right. And we see these qualitatively different features in the presence of these particles, interference fringes from classical wave interference between these dark matter waves, these cores of dark matter forming at the center of halos from these coherent oscillations called solitons, and on very small scales, time-varying granules of dark matter, which would be a source of dynamical heating in these systems. And these are real smoking gun signatures of these ultralight axion particles. But I do want to take a step back, and I think George said in the Q&A after his talk, it's worthwhile thinking about deviations from CDM on cleaner, larger, linear scales. So what is the effect of ultralight axion dark matter already in the linear matter power spectrum? Well, it causes this scale-dependent suppression in the clustering of matter. That's to say that at scales at and below its wavelength, you will suppress the growth of structure relative to CDM, which means that you form this gene scale. And here I'm showing how it depends on redshift Z, axion energy density omega A, and the mass of the particle m. The bottom is showing the effect on the linear matter power spectrum, linear order perturbations to the dark matter distribution. I'm increasing the axion mass from left to right. The bottom panels, I show the ratio to the CDM limit, where I'm increasing the fraction of the dark matter sitting in one of these axions from 1 to 8%. And we see these two non-degenerate effects. As I increase the mass, the wavelength gets smaller, the wave number of the suppression increases, and as I increase the amount of axions, the strength of the suppression at a given scale gets stronger. And in particular, we can already look for these effects in well-studied linear probes, like the cosmic microwave background, and the large-scale spatial clustering of galaxies as seen in spectroscopic surveys. But in particular, we'd like to combine the information from those probes. And so George, again, he hinted about tensions within this lambda CDM model. And so I'm forced to talk about the S8 parameter discrepancy. So S8 is this cosmological parameter that measures the amplitude of clustering around 8 megaparsec scales. And it is seen to be larger given CMB data than it is given different galaxy probes. So here, you take it to the left plot first. These are marginalized posteriors on this clustering amplitude parameter S8 and the matter energy density omega m. Yellow is the constraint given Planck CMB. Red is the constraint using one of these effective field theories. This is what Vid was talking about. It's a full shape analysis of the galaxy power spectrum and bispectrum from the final stage 3 survey, BOSS, part of the Planetary Sky survey. You see that for this particular analysis, the CMB wants this higher value of S8. Now, the fact that we're seeing some suppressed clustering at 8 megaparsec scales should make you think of the effects of axions that I just spoke about. That if you choose a mass around 10 to the minus 25 eV, these axions have a suppression scale of around 8 megaparsecs. And so indeed, when you allow this additional degree of freedom, the plot on the right, I think I've done it again. The plot on the right, the yellow contour will extend down to lower values of S8, which what is happening there is that in the presence of this axion of this mass, I can be CDM-like on the large scales at the CMB probes, but lower the value of S8 in the process. Now, the final step here would be now to fold in the galaxy weak lensing information, which is a probe of even smaller scales. And that's work ongoing with people like George, Alex, and Calvin to model the effect of those axions, in particular those wave effects on the smaller scales that galaxy weak lensing traces. But I want to show you the results of the combined analysis. So when we then go ahead and combine the information from CMB and BOSS galaxy clustering, we see no preference for the existence of axions. Instead, we set these 95% upper limits on the energy density on the y-axis as a function of the axion mass. The combined constraints are in red. For a mass less than 10 to the minus 26 eV and below, each of these can only be 1 to 10% of the dark matter today. But for an axion of around 10 to the minus 25 eV, a significant fraction of the dark matter can sit in one of these light particles. And the weak lensing information, in particular from the Rubin Observatory, will be able to confirm or refute this resolution to the S8 discrepancy. Now, as well as collecting more data, the other point I want to make is that we shouldn't pick and choose the data that we use when searching for dark matter or indeed any new physics. If we are seeing or will see the signature of some deviation from CDM at a certain scale at low redshifts, so this plot here is showing you a characterization of cosmological probes by the scale and redshift to which they are sensitive. We have this S8 parameter discrepancy appearing in low redshift information in galaxy clustering and weak lensing. We should see consistent signatures at equivalent scales at earlier times. So Vid talked about the Lyman alpha forest, and I want to show a result for some work that we did. So here, again, I'm showing the linear matter power spectrum, the top there, function of wave number. Remember, large scales on the left, small scales on the right. The bottom is the ratio to the lambda CDM limits. The black points is the measurement of the linear matter power at a wave number of 1 inverse megaparsec redshift free, given the EBOS status, that again, that's the final Lyman alpha forest set from the SDSS. The vertical line shows the measurement of the amplitude of the power spectrum. The The diagonal line shows the measurement of the spectral index, and the band shows the 1 sigma uncertainty on that. The blue line there is the lambda CDM best fit given CMB data. And you particularly see in the spectral index, as measured by Lyman alpha Forest, is highly discrepant from that inferred from Planck. And in fact, this sits at around 4.9 sigma parameter discrepancy. Now, this can be resolved by, if you take the green line, there I've put some running in the primordial power spectrum, so I allow a spectral index to evolve with wave number. That can address this tension, but you need an amount of running which is 10 times more than the simplest inflationary scenarios. And interestingly, you can also do this with a population of ultralight axions, which is the yellow line, but a small contribution, 5% at a mass of 10 to the minus 25 eV. So again, I think the last two talks have shown that we in fact already have the data from DESI, and the analysis of this coupled with more sophisticated simulations of the IGM will again confirm or refute what we're seeing in the EBOS data. But I want to make one more point about really doing this holistic, multi-scale, multi-epoch consistency check of the CDM model. If we are seeing or will see any deviations from CDM at low redshifts, we should also check that they're not messing up our understanding of the very earliest stages of structure formation. And so I want to talk finally about the UV luminosity function. So this is a piece of work done with our graduate student at Toronto, Harrison Winch. We took data from the Hubble Space Telescope. So over the last 35 years, it has measured the UV luminosity of about 24,000 high redshift UV bright galaxies, allowing us to measure what I'm showing here, the UV luminosity function. So that's the number of UV galaxies per unit volume, per unit magnitude. Remember, brighter galaxies on the left, fainter galaxies on the right, at very high redshifts from 4 to 10. So although we're not making clustering measurements, we're still able to relate the abundance of galaxies of a given luminosity to the mass of the dark matter halos that form them. And if we can model the effect of an axiom or some other dark matter model in how they either suppress the formation of small, low mass dark matter halos, or also we want to capture the way that this delays the onset of structure formation, which can indeed lead to certain scales where there's an enhancement of structure, and we can marginalize over the mapping between galaxy luminosity and dark matter halo, we can set limits on the presence of, for example, ultralight axions. Here I don't have the time for the details. We use a flexible parametric model that relates stellar mass to halo mass, which is shown to be flexible enough to reproduce the results of different hydrodynamical simulations. Okay, so once we look at those Hubble data, we do see no evidence for the existence of axions, but we are able to set the first limits on a particular range of these axion masses. So everything in solid is an exclusion from Hubble data in red on the fraction of the dark matter sitting in an axion of one of these masses. It's the first time we're able to bridge across the large-scale data from Planck and galaxy clustering across to the small-scale data in the Lyman alpha forest that Vid was talking about. And we find at the moment that it's consistent with this preference for the existence of axions in yellow that the CMB and EBOS forest data I showed you allow. And in particular, we looked in the first instance at the spectroscopically confirmed galaxies from James Webb. They're not sufficient in number yet to improve over the Hubble constraints, but if we can confirm the photometric candidates from Webb, they will have the sensitivity to look for these cutoffs that arise from the presence of axions. And so that's another future avenue of this work. Okay, I want to finish by trying to wrap this all together. This is essentially a summary of everything I've shown you. This is the axion parameter space, axion mass on the x-axis, energy density on the y-axis. Everything in solid is an exclusion. You can imagine the UV luminosity just cutting off the little white gap in the top center. And now these boxes, I'm showing you some estimated sensitivities of some of these experiments in the future, the next 10 years that George, Andrea, and Vid have been talking about. And in particular, I think it'll be the combination of these larger sets of high-resolution Lyman alpha forest data, shown by the yellow open box, and observations of the galaxy clustering and weak lensing, this 3x2-point measurement from the Rubin Observatory, and small-scale structure as seen in the Milky Way, for example, stellar streams from the Rubin Observatory, that will allow us for the first time to systematically test this dark matter model. Okay, let me summarize. So dark matter, the evidence for it goes back many decades, and the experimental program to detect the WIMP has been successful, but has returned no signal. WIMPs are increasingly excluded. And so now there's a moment for a multi-scale, multi-epoch, multi-tracer search for signatures of deviations from cold dark matter. I've talked about some of those probes. I've shown some results that ultralight axions, or indeed running in the primordial power spectrum, can alleviate some of these large-scale structure tensions that we now have in our data. And we think that stage 4 cosmological surveys, the Rubin Observatory, DESI, and Simon's Observatory, coupled with improved modeling of the baryonic effects in these systems, will be able to adjudicate the source. Thank you for your attention.